for the folks. And then you don't need to do anything. You just wait for my HFC newsletter. We're going to announce the releases in the newsletter. If you have not received my newsletter before, new participants to this series, please send me email. I will get you on the email list. With that, and please mute yourself as well. We typed the question in the chat window. We have 45 minutes for including 30 minutes talk, 15 minutes presentation. However, this meeting is going to run to 11 o'clock, Tom. If you need extra minutes within this 1 hour time, we already used a few minutes. Feel free to do so.
Okay.
With that, I will turn over to Tom, and Tom, feel free to take over. Thank you.
Okay, thank you. And you've got the title slide, okay? Good. Well, anyway, thank you everyone for attending today on one of my favorite topics, and thanks Jeff for sharing the talk with me. I'll talk for about 25 minutes, then I'll turn it over to Jeff for about 15 to talk about some current stress measurements that were just in this last August that are actually integrating civil mining and petroleum approaches. So during the COVID thing is, of course, many of us are working at home. I know some of you are probably getting back to the office, but many of us are working from home. And one of the things we miss is the morning commute. And I got to admit, when I was doing more of these stress measurements, this is a picture from one of my morning commutes. And that's a heck of a way to start a morning. It's Greenland on the way to a drill site. There's our drill site right there. And we're, oh shoot, those aren't supposed to be in there. Okay. Anyway, that's Greenland. I want to skip to another, just a couple of my favorite field projects. This one is the 2nd Avenue subway line. It's doing stress measurements for that. And this picture shows us some of the equipment and typically what a geotechnical scale stress measurement program looks like. Probably very different from what you do on your oil rigs. Our pump is this pump down here. I used to spend huge amounts of money on pressure washers, but now they've gotten so easy and cheap, I often just go and buy one at Home Depot and take it out to the job, and that's quite sufficient to do the stress measurement work. So we're on the sidewalks of New York. There's one of our impression packers coming out of the hole. And there I am with Betzel Heimson. This is about 15 years ago. Showing our flow manifold there for directing the fluid, our computer for taking the measurements. And of course, one of the advantages of working in New York is we had access to good food. On the right, you can see my trainee, and there, Betzel Heimson, Gene Sims, not sure that the fourth person is myself, are enjoying a lunch and directing the work on the project. And not every field project has this kind of amenity to it. Another morning commute. This is Changuinola, Panama. This was dugout canoes heading down the Changuinola River to our drill site. A little more primitive than the sidewalks of New York. But there's our straddle packer system there. Anyway, I thought I'd throw out a little bit of eye candy to start off the talk. Now, segueing from this, from Changuinola, the pictures of Changuinola, these is a couple of slides of the results of our testing there. And this is a large part of the civil engineering work that's done with stress measurement is for hydroelectric power plants, both the powerhouse stress measurements when it's an underground powerhouse, and also for designing the pressure tunnel, which is shown here, running along and coming into a surface powerhouse. And we did a series of stress measurements. And the key here is that the owner wants to run a steel liner through those portions where the rock stress is lower than the hydraulic pressure in the tunnel. So it's very important to establish where the cover or whatever stresses are there are less than what's in the pressure tunnel. Otherwise, fractures open up, and the least bad thing that happens is you lose a lot of water, and the worst bad thing that happens is you blow out the mountain and kill people. So this is a series of 4 boreholes that we did. And the expectation in the start of the project was where it was going to be a horizontal, a slightly graded downward tunnel with a steel liner. But what we found was that the rock stresses were much lower than we expected. In fact, in the shallower portions of this, they were even subhydrostatic. And by subhydrostatic, I mean that once we broke the rock, we couldn't even fill the borehole. The minimum stress was less than the water column to the depth of the test zone. And we found that we had a very clear stress transition. Unfortunately, in consulting projects, you don't do the work to figure out why. But as a result of this, they redesigned the entire project to run it deeper and to keep the steel liner in the better stressed rock and not go into this lower stressed region. So the reason I bring this one up to start with, before we talk about anything about stress measurements, is that these are really consequential. They're very important to successful operation of underground facilities. By contrast, this is another project which I have to remain nameless, but this is a project where we did measurements, showed low stress, and the owner was convinced that they could solve any problem like this with grouting. So they powered up the project, and the result was, and this is looking back at the back wall of the power tunnel right here. You can see this big crack in the back of the back wall, which I'm going to emphasize here. That's a hydrojack. This is a fracture that was opened up and started losing huge amounts of water when the tunnel was operating. And they had to go back in this one and put in a steel liner over part of the tunnel. It was not cheap. So by way of introduction, there are 2 key documents that govern how we do stress measurements, at least in the civil world. And one of them is the ASTM standard test method for determining rock stress using hydraulic fracturing. The other one's the ISRM suggested methods for rock stress estimation. The ASTM standard is a very important one because in civil engineering, there's often a requirement. Is it whether you believe hydrofracturing or not, whether you want to do it differently or not, or have a variant, clients require you do it to this standard. And if you do it to the standard, then you did it right. If you didn't do it to the standard, you did it wrong, and it doesn't make any difference how you did or how it came out. So the standard really defines professional practice. It's been around since about 1986, I think. It's in its 3rd revision right now, 2008, but ASTM requires that this be updated every 8 years, and it's currently withdrawn simply because it has been updated. Ingrid Tomac at UCSD is graciously, who's an ASTM member, is graciously agreed to lead the charge on getting this back into the accepted canon of standards. But at the time we review this standard, it's a really good time to look at recent work. The last one was done in 2008. They're supposed to be done about every 8 years. And among the work that's worth looking at is Lacrohani and Bunger and Detournay's excellent paper in Geophysics Journal International. Bryce Lacampion's work we heard about last year. Lots of new developments in petroleum practice. There's been a lot of new thinking about hydrofracturing and stress measurement. And I think it's a good time to review where we are. So in this talk, I'm mainly going to focus not on every aspect of hydrofracturing, but especially on alternative shut-in pressure interpretations, which is how we get our minimum stress. I'm going to focus in on some stress measurements that are being done for the Sanford Underground Lab in South Dakota for the CoLab project, where we are merging civil and petroleum protocols. And Jeff Burghardt will talk about this part. I would also mention that there's similar work to this being done by Kai Brooker, who's just finished up a master's thesis at ETH in Switzerland at the Pedretto Underground Lab, a similar facility to Sanford for geothermal research. So as Joe mentioned at the beginning, I think it's a very good time to encourage the ARMA community to participate in these standards, because this is, after all, our profession. So briefly comparing civil and petroleum approaches, petroleum is almost always in sedimentary rock, except for some mini fractures. Usually it's done at higher rates, and a lot of concern about fracture extent and very complex shut-in pressure analyses. by comparison, civil engineering uses lots of rock types, but especially lots of hard rock like granites and metamorphic rocks, usually very, very low flow rates, like 0.5 to 5 liters a minute. However, leak off, which is usually ignored, and I always thought it was negligible, is actually quite significant at these low flow rates. Fracture size and stress measurement is usually not a concern, and the shut-in pressure analyses are usually very, very simple, as we'll see. I'm going to skip over this a bit quickly, but briefly, hydrofracturing as a stress measurement technique really comes out of work in the 40s through the 60s, particularly in the 1950s. M. King Hubbard and A. Scheidegger looking at injection pressures from petroleum wells and seeing that you suddenly get great increase in rate, said this might have something to do with stress. And then in the 1960s, Charles Fairhurst had a very significant contract with the Corps of Engineers to look at determining rock stresses at great depths. Prior to that, overcoring was just beginning to get started to be used in the 1950s. There wasn't a deep rock stress measurement, and what Fairhurst came up with was hydrofracturing. And he had a brilliant group of students. It's hard to imagine being a fly in the wall in that grad student office with Betzel Heimsen, Jean-Claude Rogier, Fritz Rummel, Francois Cornet, not to mention Bill Husterlid, and oh my goodness, the people who were there are just amazing. And then beyond that, in the 1970s, hydrofracturing started used in some very significant projects like the Rangeley oil field experiments, the Helms pumped hydro project in the mid-70s, and Mark Zoback started, and Steve Hickman started doing this for seismicity and earthquake studies, world stress map, and a lot of it got established, I think, in a 1981 National Academy workshop that Mark and Betzel Heimsen chaired. Yeah, Rangeley, very briefly, this should look very familiar, but pore pressure and earthquake generation and knowing the stresses for that, that's the early 1970s, one of Betzel's first big projects at Wisconsin. Helms pumped hydro project in 1974, the first major application to a hydroelectric plant, which also had a big effect on its design. So in terms of the basics of stress measurements, I think this should look pretty familiar. When we do a stress measurement like a mini frac, we have a first cycle with a breakdown pressure. We pump a little bit, shut it in, reopen the fracture, pump a while, shut it in, and then we'll often do some kind of stepped injection test to get a pressure flow plot. And we analyze this through the standard Cure solution, the breakdown pressure being related to the minimum stress times 3, the maximum stress -1, plus a tensile strength and a pore pressure. All these terms have a lot of uncertainty to them, but that's pretty much standard practice. This is one of our examples from the Surf Underground facility, which is pretty standard. Breakdown pressure with a relatively shutting quickly, reopening, looking at where we start to deviate from the compressibility effects of the system, get a shut-in pressure here, and repeat this cycle with, in this case, about 4-minute shut-ins, and the whole thing takes about 30 minutes to run. I'm going to skip over this part about the fracture mechanics solution. I'm very enamored of Rummel's fracture mechanics solutions. Basically, what Rummel came up with was a similar thing where breakdown pressure was also related to sigma H min and sigma H max, but with two constants that replace the 3 and the -1, or actually they're functions of the initial crack length. And the tensile strength term becomes this thing, which has fracture toughness and borehole radius in it. I'm going to skip over this a bit in the interest of time, but one of the things I wanted to show is a consequence of Rummel's, this is a bi-wing fracture, but it also holds for a radial crack, is that as your crack gets larger or you extend your hydrofrac, the hydrofracture extension pressure drops pretty close to the minimum stress. Net pressure goes very close to 0, and effective tensile strength gets very, very small as well. When you look at those things, this is for, say, this particular calculation is for a fracture toughness of 1 MPa per square root meter, which is a pretty typical number for laboratory tests. What this tells us is that as the fracture gets larger, net pressure pretty much disappears, at least by this way of seeing things. So I wanted to keep that thought in mind as we go into looking at shut-in pressure. So this is a typical shut-in pressure curve on a cycle. We have our buildup, we start extending the fracture, we stop pumping, there's an instantaneous shut-in pressure, that quick drop, and then there's some kind of slow leak off that continues afterwards. I'll come to the part of the right in a little bit here. Two very key papers in this for civil engineering are Mu Lee and Betzel-Heimsen's paper on statistical evaluation of hydraulic fracturing stress parameters, primarily looking at shut-in pressure, and also Kazuo Hayashi and Betzel-Heimsen's paper in Journal of Geophysical Research from 1991. Now, the analysis of shut-in pressure in civil engineering can be very, very crude. I won't say where this one is from, but just start being something as simple as drawing straight lines and looking at intersections. No other analysis done here, and there's your shut-in pressure. But overall, in civil engineering, the way people have been doing this is that you're looking for two lines. And an interesting assumption, I didn't realize this till relatively recently, that we've always kind of assumed that the shut-in pressure curve had a rapid decline at first, followed by a slower decline. And it was assumed that the minimum stress was where there was a transition from that rapid decline in pressure to a slower decline in pressure. And there are tons of ways that people have done this in the past. So for the y-axis, this would be pressure, and people plot that against time, log time for radial flow, square root time for linear flow, recovery time, and just every imaginable thing you can think of, exponential, just to look at this linesmanship. Or looking at the rate of pressure decay, either dp dt or dt dp, and then comparing that to pressure. So, but a common thread through all the civil engineering things is that you have a steep rate and then a shallower rate, and shut-in is where that transition is. So that's there are a variety of more and less sophisticated ones. Probably the most sophisticated one is Hayashi and Heimsen, which uses Nolte's leak off, but uses it in kind of an interesting way. Hayashi defines a number of stages here where before shut-in, the fracture is open, then you shut in, and then the aperture decreases, and then the fracture closes from the tip on in. So that as the fracture is closing, it's closing from the tip towards the hole, and then when you get complete closure, the fracture becomes pretty much impermeable, and that's where he defines his key points in his shut-in curve. These are his different stages. And here are some examples here where he defines, again, this is the rate of pressure decline, but where you see the steep and then the shallow, and the transition is that shut-in pressure. Here's another example from Lee and Heimsen plotting the dp dt against P. And again, it's the change in the rate that is the shut-in pressure. Well, going ahead to the oil and gas view of the world, in the oil and gas view, you have an ISIP, and this is from Warpinski. You have a leak off, and then at some point, the fracture closure, the rate of decline actually increases. And that's a big distinction to the way civil engineering looks at these things. Again, you have an increase in the rate. Now, why does that happen? Well, I'm not going to go into the details of G functions and pressure transient analysis, but the key thing, the way I think of this, is that it imagines the fracture is open, and while it is open, the fracture is acting as a pressure reservoir that maintains the pressure in the fracture. And once the fracture closes, the overall compressibility drops, and therefore the leak off has a much bigger effect on the pressure at the borehole. A way to think of this is if you imagine that you were sitting on an air cushion. Imagine you're sitting in your seat right now on an air cushion. The pressure in the air cushions, whatever the load of your body is, and we won't go into the details of what the load on your body might be on it, but the load of your body. And then if you were to start cracking the valve on that air cushion, it would be leaking, and the rate of pressure decline would be very, very slow because you would be maintaining the pressure of your body weight. But once your butt touches the seat, that increase goes much, much faster. So you might think of it that way as a distinction. So there's an increase in fracture rate at closure. So again, showing it this way, you have the open fracture just after ISIP. The fracture closes right here. And all the while, these red arrows indicate leak off into the formation. If you go long enough, this becomes radial flow. I think I'll skip over this, but one of the key things are Carter's leak off, which was looking at this during the fracture extension, and Nolte extended Carter's concepts to the shut-in period. And all this is predicated on a square root time leak off behavior, but where the clock on the square root time transient is changed starts every time you add a fracture increment. Okay, so just to summarize this, civil engineering, we have this fracture closure where things are where there's a change in lower pressurization rate. Oil field where it is an increase in pressurization rate, again with these sort of different concepts. So what is the significance of this? In the oil business, these occur at lower levels where this closure happens. So it means the difference between propagating pressure and closure pressure in civil tends to be very, very small, like that Rummel thing I showed earlier, where for 1 square root meter, 1 MPa per square root meter, this is a very, very small number. You start to decrease where the fracture closure is, and net pressure becomes a much, much bigger number. It also suggests that fracture toughness may be larger than what we get in the laboratory. It suggests that civil methods may be overestimating minimum stress by MPa or more. So, and this has a strong effect on predicting fracture extent. I'm going to segue now into the CoLab experiment. I hope I didn't go through that too quickly. But the CoLab experiment is at the Homestake mine, which was closed in 2002, the U.S.'s deepest gold mine. It had a variety of physics experiments and was in consideration for a big deep underground science lab in 2010. More recently, Lawrence Berkeley Laboratory had a fracture generation and monitoring project in 2016-17, and that morphed into the current CoLab project, which is going on at the Sanford Underground Lab. There's a picture of the 4850 level where the work is happening, the shaft, and there's the Black Hills in South Dakota for reference. There's a lot of cast of characters with this, supported by the Department of Energy, and a lot of institutions are involved in it. It's a very large cast of characters. Some of the key people are Tim Nesi and Pat Dobson from LBL, Joe Morrison, who you just heard in Peng Cheng Fu, Matt Ingram, Doug Blankenship from Sandia, Ankur Singh, Mark Zobak from Stanford, Bill Roggenthal, South Dakota School of Mines, lots of people. And in the background, you see the expert on-site advisory committee, blue ribbon people all. So the CoLab is at 4850. There's a cross section of it. Here's the Ross shaft here. That's this guy there. The Kismet project, those little red things are the hydrofracts we made for stress measurements. And there's experiment 1, which got finished up in the fall and we're moving because of physics experiment demands to the 4100 level to experiment 2, which is up here by the Yates shaft. The goal of CoLab is to establish fluid circulation through a hydraulic fracture, monitor it with geophysics, and do tracer tests and other thermal circulation tests to look at heat exchange. That's why the geothermal thing is important here. Some design issues are that we need to establish a fracture connection between the injection well and the monitoring well, which are 10 meters apart. We're not using proppants, so in order to have a circulation, we need to maintain a sufficient rate to overcome the leak off, and we need to maintain a sufficient pressure that keeps the fracture open, but we don't want this thing propagating to the drift. And here's where net pressure comes in. If net pressure is large, then we can make much less likely to extend this thing to the drift. That is the difference between propagating pressure and closure pressure, because we want to be doing this experiment between the propagating pressure, lower than that, and greater than the opening pressure, or greater than the closure pressure, excuse me. So between closure pressure and propagating pressure. If net pressure is small, it's really hard to hit that, especially if the stress is heterogeneous. If it's large, this becomes much easier. So here's an example of what we had to work with to design this experiment. There's a breakdown pressure. This is one of our Kismet stress tests Again, I showed this to you earlier. And Mark McClure, who I forgot to put Mark on that list. He's a key person in this project. Took a look at that. And he said, can I look at that data? And he said, you know, with these 4-minute shut-ins you're doing here, my G-function analysis says you didn't close that fracture. You didn't reach minimum stress. And he said that your net pressure, our net pressure would have been probably the order about a 0.2, 0.3 MPa or less, whereas the net pressure that comes out of this is around 1.5 MPa, or it could be greater, with about 2 microdarcy permeability. And that to do this right, you need longer shut-in times. So that really got us thinking about this. Again, to get back to this idea of fracture extension. So when we've gone we've done a new set of stress measurements at the 4100 level, and this is the stress we have so far. These are the Kismet measurements at 4850. The Yates amphibolite measurements were in a different rock at 4100. And interestingly, we've got this rhyolite dike here that seems to have lower stress. It has a very strong contrast in this figure here on the right shows dynamic elastic modulus, and there's ISIPs. But anyway, this is and very consistent orientations, not identical, but very consistent. So in doing the measurements of the 4100 level, we decided that we would start to incorporate some of the oil field protocols and as perhaps preparatory towards modifying the ASTM procedure. So I think with that, I'm going to go ahead and hope we didn't run too badly into Jeff's time here. I'm going to go ahead and flip to Jeff's talk. And Jeff, if you could unmute Jeff and put him on, he will continue.
Thanks, Tom. So, excuse me. So yeah, I'll go into some of the details from this 4100 level measurements that we made as part of the collab project. Want to recognize, Tom obviously helped design and execute these tests. Matthew Ingram from Sandia National Lab, as well as Bill Rogenthien, not listed here, and Carson Reimers from South Dakota School of Mines helped also execute these tests. So let's go ahead and move on to the next slide, Tom. So we did, because this is a research project, excuse me, and not the sort of production commercial stress measurements that Tom's usually making and talking about here, we did have some freedom to try several different test methods and compare them. So we did shut-in tests, so it's a conventional sort of shut-in pressure decline test, flowback test, hydraulic reopening tests. We did one sleeve reopening test and some step rate tests. And I'll talk about each of these in detail as we go forward here. Next slide. So just at a high level, this is a table. Not going to go through the whole thing, obviously, but these are all the different depths we made stress measurements. So these are measured depths from the drift floor. So again, it's nominally 4,100 feet below ground surface, and then is where these measured depths are referenced. And I guess the first thing I would point out here is the, excuse me, the reopening tests and the instantaneous shut-in pressure ISIP tests. I have labeled here as being 100% successful with the caveat at the bottom. The fine print is I'm talking in terms of these tests yielded interpretable results, not a statement on the quality or meaningfulness of that result. Whereas the flowback and the shut-in tests often yielded ambiguous results, so uninterpretable results, and I'll show those later. So that, for cases where you absolutely must have an answer, that's a big drawback, and I'll talk about why, maybe some of the factors that led to those ambiguous results later. The other thing to mention here is it's useful to step back and take a look at the big picture. So the difference between the the different measurement techniques, you know, they differ by typically less than 2 MPa. So kind of you have to step back and ask yourselves what level of effort that extra accuracy is worth. If you're designing a, you know, pumped hydro station and you're going to slap a significant safety factor on it anyhow, it may not be worth worrying too much about this. Whereas, you know, if you're talking about fracture height containment, 2 MPa stress difference might make all the difference in the world. So, okay, next slide, Tom. So just, Tom already talked about a bit of this, so I'll go through this pretty quickly, but just to think conceptually about this at a high level, if you imagine your wellbore and fracture as a pressure vessel, so ignoring leak off for the moment, and you can add fluid to that with a pump, and then we're measuring the pressure. The derivative of the pressure with respect to the volume gives you this compressibility, and it's the sum of the compressibility of the wellbore, and by wellbore I'm including, you know, all the hydraulic lines, pumps, etc., and the compressibility of the fracture, CF. In the next slide, Tom. And so this is a very busy slide, but and Tom already kind of talked about this. If now talking about leak off, when you shut in, you're losing fluid through leak off, and as Tom mentioned, at each point in the fracture, the time that the leak off began is different. And so if you integrate this Carter leak off velocity over each little patch of fracture, that's what ultimately leads to the G function. And when the fracture is open, then the derivative of pressure with respect to G, because remember G is essentially proportional to the rate of fluid loss, is constant. And that's assuming the fracture is not continuing to propagate and any number of other things. And so the concept here is that when the fracture closes, that compliance of the fracture, you know, it's closed, so it essentially it becomes very large, or sorry, very low compliance, very high stiffness. And therefore the rate of pressure decline will accelerate. Now this is true for low permeability formations. I have a reference here to Mark McClure's 2016 paper, which is useful to get more into these details about, and specifically how things differ for higher permeability formations. But this is the general concept of how these shut-in decline curves are, at least in the petroleum community, as Tom pointed out, are conventionally interpreted. Next slide, Tom. So I'll show a few results. So these are two different depths, so 44.7 meters on the left, 19.7 on the right. And the left, I'm arguing, is a fairly nice test with a fairly easily interpretable result. So, and there should point out there's quite a bit of debate in the community about how to interpret these things and where to pick closure, and that's not really the point of my talk. So I'll recognize there are arguments to be had about where exactly to draw these lines, but generally you can see at early times there's a rapid decline in pressure, and that's, you know, generally thought to be the result of continued fracture propagation. Then it settles into kind of a linear trend, and then at some point the slope of the curve becomes more negative, and that is consistent with a decrease in system stiffness, or sorry, increase in stiffness, decrease in compliance, that would be a result of fracture closure. Contrast that with the curve on the right, where then this was actually an overnight shut-in, so this was a very, very long shut-in, and you can see the slopes just continuously decreasing, and there's really no signature consistent with this sort of theoretical idea of what we would expect. And in this case, as I'll show on the next slide, it's what I think the most likely reason for this is I don't think the fracture closed during that overnight shut-in. And so that's a very long shut-in, but we're dealing with a very low permeability system here. So to talk now about a different kind of test that's similar is a flowback test. And so, well, go back to the previous slide, Tom. Okay. So in this case, the idea is we're going to flow back the well. So Q flowback is the flowback rate, such that the flowback rate is considerably larger than the leak-off rate, and in which case this leak-off isn't so important. It's mostly the flowback. And done properly, the flowback should be much larger than the leak-off rate, but not so large as to create large frictional losses inside the fracture. And of course, it's difficult to know these things a priori. So there's often quite a bit of iteration that's required to get this right. So even though it's a nominally a much quicker test, it's one that's a little more difficult to get right. Okay, Tom. And so here's two flowback tests. So the one on the right, I'll start there. This is that zone the same zone that we had shut in overnight and I think did not close in the overnight shut-in. And basically here you can see there's a clear knee in the pressure around 18 MPa, which if you remember on the two slides ago, in the overnight shut-in, it did not drop below 20 MPa. And so this is a fairly nice interpretable result. Whereas on the left, this is another zone I showed earlier, 11.9 meters measured depth. And just a note here, the flowback I'm plotting versus volume. So we didn't have great flowback rate control. It was just through a needle valve in a fixed position. And the data was quite noisy, so some shortcomings here. So what I did is integrated the flow rate to give a volume and plotted it versus volume. And so this test did have a brief shut-in before we started flowing back. And so this is, you can see on the left-hand side of the curve on the left plot, there's a sharp decline in pressure before it starts at a constant volume. And that's the shut-in. And what I think happened here is the fracture closed during that brief shut-in, so that when we started flowing back, the fracture was essentially already closed. And then we had just this linear curve of pressure versus flowback volume. So this is kind of a lesson learned, and we were kind of trying all these different methods, but it's often not advantageous to get greedy and try to implement two different methods and do a brief shut-in before a flowback, because you're often left with two uninterpretable tests. So it's for flowback, it's best to start flowback immediately, because otherwise you risk not having a good shut-in result or a good flowback result. All right, next slide, Tom. So just briefly, hydraulic reopening tests. So we did these, and again, these interpretation of these curves is it's a continuously varying slope. So where exactly you pick the reopening is there's plenty of room for debate there, but there it's always an interpretable result in some degree, to some degree. So these are our two examples. The one on the left was after a brief shut-in, then we just started pumping again, and the one on the right is starting from zero pressure. And in this case, the flow, this is that same depth zone at 19.7 meters where we did the overnight shut-in, the flow back, and you see the reopening pressure is very similar to the closure we saw in the flow back test. So further evidence that most likely it did not close in the overnight shut-in. Okay, next slide, Tom. So a few drawbacks to the hydraulic reopening tests. that are, conventionally they were used to give information about the intermediate or maximum horizontal stress, the vertical well. There's lots of reasons to think that's not a good approach. One being the residual fracture conductivity causes the fracture faces to be loaded, and then you're not dealing with a Kirsch solution, and therefore, most of the interpretation methods are based on a Kirsch solution, so that kind of invalidates that approach. Another more recent, and Tom mentioned the same paper, really nice review of these methods, is the effect of wellbore storage really obscures the reopening pressure because it sort of smooths out and obscures what's happening at the fracture due to the compressibility of the system. Now, that paper does have some nice dimensionless parameters that you can evaluate to see how big the wellbore storage effect is. And we've not computed those parameters for our testing yet, but given the small volumes and the fact that we're fairly close to the testing intervals, our compressibility is relatively small compared to other field scenarios. So with all those shortcomings of hydraulic reopening tests, an attractive alternative is a sleeve reopening test, where basically you're reopening the fracture with packer pressure. And I meant to give an acknowledgement earlier. My mentors when I was at Schlumberger, and I noticed he's on the line today, Jean DeRoche, helped introduce me to this method and helped give us some guidance on designing these tests. So thanks, John, for that. And so next slide, Tom, I'll show a sleeve reopening result. So on, excuse me, the left is a hydraulic reopening that I showed previously at this 11.9 meter depth. And on the right is a sleeve reopening on that interval. So what we did is after we generated the fracture, we tripped the packer up so that the lower packer element was over the hydraulic interval that we had just broken down, and we inflated the packers, and this is a plot of the packer pressure versus packer volume. And what we're looking for here is a decrease in slope that would be associated with an increase in compliance of the system resulting from the fracture opening. And so you can see I've drawn a line here at about 20 MPa, where and the orange curve is the slope. So the slope decreases by about 50% at this point. And this is a little bit lower than the range of pressures where we saw the hydraulic reopening. But yeah, so this test, because it doesn't load the fracture faces, the Kirsch solution is still nominally valid, although in this case, the fracture was significantly oblique to the well, which is another can of worms I won't get into now, so it complicates the interpretation a bit. But this was a nice, straightforward method that I think really overcomes a lot of the problems of the hydraulic reopening test. It does come with a little bit of extra risk of getting your tool stuck because you're pressurizing your packers quite a bit higher. But other than that, it's a really nice test method that we hope to use more in the future. All right, next slide, Tom. So just some quick conclusions from this testing program. The ISAP is quick, and it's very robust in that it's it's very rare for it to not yield a interpretable result, and very well may be good enough for many applications, but not all. So I guess you need to ask at the project level what level of accuracy is required. Shut-in pressure tests can require very long shut-in times in these low permeability formations, which turns into a lot of money, a lot of rig time. They often yield ambiguous results that are difficult or impossible or subjective to interpret. Interpretation of these tests remains subject to significant debate, and different communities have approached them obviously from different ways. So different experts will give different opinions, which is, I guess, tough to deal with, and it's understandable why, especially in the civil community, they've migrated more towards ISIP because it's less ambiguous, and that makes contract writing much easier. So flowback tests are a much quicker alternative, especially in low permeability formations. But again, selection and control of flowback rate is essential and may require some iteration. So that recent paper I mentioned does provide some nice guidance on what, some dimensionless parameters that help anticipate what flowback rates will both substantially exceed the leak off rate while not causing too big of viscous pressure losses in the fracture. So there's some nice guidance there, but they can require some iteration. By the sleeve fracture reopening tests, we're also very quick and simple, and I think are a better way to try to deduce the maximum horizontal stress. Much more reliable than a hydraulic reopening test. I think that is my last slide.
Okay, I'm sorry if we've run a bit long here. I do have two more really quick slides to show. And there's some other work that's going on that, in addition to the tests we're doing, the CoLab project is also applying the SimFip tool of Yves Guglielmi at Lawrence Berkeley Lab. SimFip is a tool that measures between two packers all of the displacements that are happening around that fracture. So this is a means we're currently analyzing results from that same hole, some more tests, but this has the potential for giving us a direct measurement of fracture opening and closure to supplement or complement the various interpretations of the pressure time records. This is Jonathan Aho Franklin's AGU poster, and I mentioned before that we have a very highly instrumented test bed for experiment 1. It includes active seismic monitoring, so we're able to see changes in seismic velocity as the fracture closes, in addition to microseismics. See how the fracture is closing from the seismic velocity field through the rock. So these are things that are still under analysis, but I think our other outcomes of CoLab could be very consequential to these questions. So I've run a little bit long here, but I guess we should take a look at our comments. And do I stop sharing or just start looking at comments?
Yeah, thanks, Tom and Jeff. And feel free to address the questions, couple of questions in the chat window. For the folks, we're going to release the slides and recordings. Thanks, Tom and Jeff's generosity through the HFC newsletter. Tom, go ahead.
Stop share. Okay, so I stop sharing now. Okay.